So whenever you attack a trig question, you want to be thinking of identities. It doesn't always play out that way, where you can simplify things to a point where it becomes nice and easy. But if it's ever going to play out that way, it'll happen just based off of your knowledge of those trig identities. Right? In this case, we're not talking about complicated stuff like the Pythagorean identities or double angle rules or anything. It's reciprocal identities. So cosecant, by definition, we know cosecant is equal to 1 over sine. So before we even get into the calculus, I would look at this as cosine of x divided by 1 over sine of x. All right. Now, keep, change, flip makes this sine x cosine x. All right. Now, this is in the lesson related to chain rules, so you would think that there would be some chain rule component to it. And there is, it's just kind of hidden. You can solve this problem. You can come up with the derivative without touching the chain rule. So I'll show you both ways. One way is nice and convenient, but only if you recognize it. The other way, you'll get the correct answer. It'll just take you a couple extra steps. All right. So if we're looking at this with the product rule, I have my two factors, sine of x, cosine of x. So g prime of x would be the first function, sine of x, times the derivative of the second function. Derivative of cosine is? Negative sine x. Very good. Plus the second function, cosine of x, times the derivative of the first function. Derivative of sine is? Cosine. All right. Now, simplifying this, now it's not a requirement that you simplify, but when I show you the other method, I want to show you how the two relate to one another. So we would call this a final answer. And again, we didn't even touch the chain rule here, so you're like, oh, it's not relevant. It is in a sec, you'll see. All right, so this is the same as negative sine squared x plus cosine squared x, which in turn is the same as cosine squared x minus sine squared x. Close. Right idea. It's an identity. If that were a plus sign in the middle, then it would be 1. But this is actually the double angle identity for cosine. All right. The issue with the double angle identities is you learn it. Algebra 2. I forget which gap course it's in, but it's in one of them. You learn it, you use it for a little while, then you don't use it for a very long while. Then you come back to it, use it for a little while, then you don't use it for a very long while. And now here we are again, and you look at it and say, oh, okay, it's a rule, great. But it's not the kind of rule that you would think, this is something I should look at a formula sheet for. Like back in Algebra 2, I think Algebra 2 still does that, and pre-calc. They're like, oh, here's a little reference sheet for you. Just look up your identities on it. It'll be good. The problem is if you don't know enough to look at the reference sheet, then it's all over. Right? I'm not saying you need instant recall, but you kind of need like instant, I know this is a thing. It's a little different. But what I have shaded in gray there is really all you needed. You didn't need to go this far. But let me show you how we could have used the chain rule here. Now, most people early on in learning about rules of calculus, derivative rules and chain rule and product rule and all that stuff, you kind of look at it and say, well, let's go back to the power rule. I like that one. That's the easy one. Then you're like, all right, well, if I can't use the power rule, I'll use the product rule because that's not that bad. And you kind of shy away from the more complicated ones. But the more experience you get with the different rules, the more you realize they're all just rules. So what difference does it make? Right? It's the nature of the function that drives the difficulty level. right? If it's a complicated function, that will force you down a path that will be more complicated than if it were a simpler function, right? It's not like, well, this is a chain rule problem. It's more like, this is a nasty function. What technique can I use? Chain rule in and of itself is not overly complicated. It's when it's applied to a messy function, that's when it gets complicated, all right? So going back to this g of x, I'm going to kind of look at it. Oh, that's not a marker. I'm going to look at it as a form of an identity. We had sine of x, cosine of x. Now, you might remember a rule. Sine of 2x is equal to 2 sine x cosine x. The double angle rule for sine. That's almost what we have here. So close. That little 2's in the way. So I look at it and say, well, let's get rid of that 2. And how do you do that? Well, an identity is an equation. We're not verifying identities. We can cross the equal sign because we're not making a proof here. What I would do is I would just divide both sides by 1/2, or I'm sorry, divide both sides by 2, which would make it a coefficient of 1/2. So 1/2 sine 2x and 2 sine x cosine x are the same thing. So g of x can be thought of as that. And you can kind of look at this and say, well, this is way too much work. I would never do it this way. It's not too much work if you know the identities, because a lot of this stuff is happening in your head. You know, like this, I would never write this down, right? But that's because I know the identities, all right? Once I got to this step here, I circled everything, so that doesn't help. Once I got to this step here, I'd look at that and say cosine 2x. I wouldn't write everything that followed that. I'd look at it and say, okay, well, if I multiply those two things together, I'd get a negative there, a plus there. When I move some things around, oh, look, that's cosine 2x. But only because I know the cosine 2x rule, all right? So it helps to know these identities. Because now, when I go to take the derivative, g prime of x, I'm looking at this using my blob method. I'm looking at this and saying, all right, I got 1/2 sine of blob. All right, the derivative, well, the 1/2's coming along for the ride, of the sine of blob would be what? You got to say it. Cosine of blob. Requirement that you say the blob. All right, cosine of blob. And that blob happens to be a 2x. As long as you know to multiply by the derivative of blob, which in this case would be a 2, you'd have your result. All right, clean it up a little bit, not too much. Really, just the 2 and the 1/2 canceling away, but ultimately you'd get this result here. All right. But if you look at the process that we followed in terms of finding the derivative, it was much simpler. Simpler as in writing less physical characters. All right, conceptually, I mean, there's a little bit more to it, but if you know your identities, it makes things a lot easier. All right, good question. Find derivative, but specifically at a point. So you're going to have to evaluate this this derivative, right? Now, since it's a function of x, I'm only really interested in the x value of the point that they give us. So, yeah, they gave us the y value, which is wonderful, but it's irrelevant to what we're looking for. If I needed to write the equation of the tangent line, then that's useful information. All right, but finding the derivative, I'm going to write f prime. Well, actually, even before that, I'm going to rewrite the function in a friendlier form. 1 over x can be thought of as x to the negative first. And the square root of cosine can be thought of as cosine of x raised to the 1/2 power. All right. So when you're taking the derivative, We have names for every rule, but sometimes they're a little bit more intuitive. It's the sum rule for derivatives, but it's basically telling us that we could take the derivative of each of these two functions separately and then add them together later on. All right, so I have this function, which is a nice, easy function to work with because it's power rule ready. I have an understood coefficient of 1. So my derivative here, f prime of x, would be negative 1x, or just negative x to the negative second. So that's nice and easy. We don't have to worry about power rule, product rule, or quotient rule, or chain rule. All right, but for the other one, it's not really the nicest function in the world. The square root of cosine, or cosine to the 1/2 power, is a function raised to the 1/2 power. All right. Now, in an ideal world, that function would just be x to the 1/2 power. It'd be nice and easy. It would be power rule ready. All right, not the case. So whether you like the U substitution method or the blob method, we're going to have to go after this using chain rule. All right, so I like the blob method. All right, so I have blob to the 1/2 power. So the derivative of that would be 1/2 blob to the negative 1/2 power. All right. With that blob itself being cosine of x. All right, my color choice is probably not the best here. I'll go back to black because I can even barely see that. All right, so then as long as you remember that you have to take the derivative of the blob and multiply it on at the end, then you'll have your chain rule derivative of cosine to the 1/2. And the derivative of cosine is? Negative sine. All right. All right. Now, we have to find the derivative at the point, pi over 2. All right. Now, it's up to you if you want to simplify first before getting into that. It's really up to you. Because for numerical cases, I said it and I stand by it. You could just do it on Desmos, right? But sometimes it gives you an answer that's not the most appealing looking one in the world. So, you're a little suspicious of it, so you try doing it by hand just to make sure, all right? And also, it's a skill, so why not? So I would pop in the pi over 2 everywhere I have an x. And as long as you know a little, I'd say very, very basic unit circle. This is just the quadrantal stuff, the ones that are on the axes, not even the meat and potatoes of it. And it's just like the plate. There's no food on it yet. All right? It's 0, 90, 180, 270, 360, just those angles. So I'm only concerned with the 90-degree angle. So if I know what the cosine of 90 degrees is, I'm going to be in pretty good shape. Same thing with sine. Cosine of 90 degrees is what? 0. Sine of 90 degrees is? 1. So I have a negative there, so it's going to be negative 1. All right. Now, negative paren pi over 2 to the negative 1/2. Negative second power. If I simplify this, I'd get my answer, but a little number sense goes a long way. If you recognize the negative exponent associated with that 0, negative exponent tells you to take the reciprocal of 0 to the 1/2 power. All right, the reciprocal of the square root of 0. Well, the square root of 0 is 0. The reciprocal of 0 is undefined. All right, so this whole thing is going to boil down to being something that is undefined. All that for a drop of blood. All right, so, you go to Desmos, f prime of x, well, f of x first, but then f prime of x will give you the derivative function's graph. It won't give you the equation, but it'll give you the graph. And you could put it in, Desmos is nice like this, you could put it in a friendlier looking form. This is what the graph would look like. It's pretty awesome looking. All right. So just make sure you're in the appropriate mode. In this case, Desmos is defaulted to radian mode, so I'm not worried about that. But if they said find the derivative at the point 60 degrees, comma, whatever, then, make sure you make the adjustment. But f prime of x, if you wanted to look at the graph, looks like that, very tangential. That's not really an appropriate word here, but it sounded right. It sounded fun. It's tangent-like. It looks a lot like a tangent graph, cotangent graph, actually. All right. And if you simplify the cosine sine ratio and the derivative, you do get something that has tangent aspects to it. But that's not why we're here. We're here to determine what f prime of pi over 2 would be. And it says undefined. All right, so that's great. Verifies our answer on paper. But then let's take a look at the function itself when x is equal to pi over 2. All right, so let's type in x equals pi over 2 and see what's going on there. I know it's kind of tough to see, so I'll bring it in. I'll make this dashed. I'll make dashed is fine. All right. At that location, you could see that it appears to be going vertical or approaching a vertical asymptote. It's kind of hard to tell without really investigating this function. There's definitely a break in the graph. Without seeing what would happen in that break, in the infinitude of that break, like what that infinite space between the curve that exists coming into pi over 2 and coming out of it looks like, it's kind of hard to tell, maybe 3 pi over 2. Like all of that, what's going on in there? I don't know if it's going to just go vertical or if it's going to approach a vertical asymptote. I don't know what's going to happen there, but it does seem to be a pretty reasonable justification of the undefined derivative, right? So visually, something funky is going on at pi over 2, and that's usually good enough for most people. All right. So I told you to skip 13-14. Another one that folks typically have trouble with would be number 16. 17's asking the same thing, but with a simpler function. So, you would think that would be easier, but trig functions are their own animal. So, determine the points at which this function has a horizontal tangent. Now, horizontal tangent, horizontal has a slope of 0, horizontal lines. Since a tangent line, when you're talking about the slope of a tangent line, the derivative, it would make sense that we would find the derivative of this function and set it equal to 0. Easier said than done in most cases, but that's a pathway to getting this correct. All right. So here I'm looking at something that can be written as a product if I bring that radical up to the top and negate the exponent. That's going to be a nasty product. I don't know if I'm really interested in that. All right. So I'm going to look at this with the quotient rule. So I have the top as one function and the bottom as another function. All right. Now the formula is the formula, but if you looked at the quotient rule or the videos, you see, there's mnemonics that help you remember it. It's low d high minus high d low over the denominator squared, and away we go. So when I say low, you say go. No. When I say low, I mean the bottom of the fraction. When I say high, I mean the top of the fraction. So low d high. So I replicate the low, the denominator, rad 2x minus 1, multiplied by the derivative of the numerator. I'm going to use the notation here for now, at least for this one problem, minus the high, d low, meaning the derivative of the denominator. over the denominator squared. And away we go. And so this is what we have to simplify. Parts of it will be nice and easy, and parts of it will be not that. All right. So first off, I see that I have a radical and a power of 2. Radicals, powers of 2, opposite operations cancel each other out. That's wonderful. The derivative of x is equal to 1. All right. Whether you're using the power rule or just looking at the simple ratio, dx over dx, dx divided by dx. The letters dx divided by the letters dx, they would all cancel out to just a 1. All right. So I'm looking for the derivative, well, derivative within a derivative. It's kind of weird to think of it that way, but that's really what we're looking for. So that first part, square root of 2x minus 1, minus x times the derivative of this, but I want to put it in a friendlier form. 2x minus 1 to the 1/2 power. And the whole thing is just going to be over 2x minus 1. Now, the chain rule shortcut, it really is optional. Like, some people just don't like it. But you get to a problem like this, and really it's kind of an instance where the last thing you sort of want to do is have to do the chain rule out in its full glory off on the side. Right? It's fine to do that, but it takes a little doing. And so maybe you want to, maybe you don't want to. Maybe you're all right with it, but most people are looking for, like, all right, this problem's got enough writing as it is. Let's use a shortcut here. All right, so that's why I introduced the blob approach, because it takes out a little bit of the writing. And if you really think about it, we've talked about this a little bit, but if you really think about it, it's the same concept as U substitution, exactly the same, except instead of using a U, we're using a blob, and we're just doing a lot of stuff behind the scenes. All right, so rewrite. Oops, center marker. Square root of 2x minus 1 stays as is, minus x. But now I need the derivative of blob to the 1/2 power. Now it's very similar to what we just did in the previous problem. Blob to the 1/2 power, or something to the 1/2 power, would be 1/2 of that blob. Oh, I lost a 2. Get back there. 1/2 of the blob to the negative 1/2 power, with that blob really being the 2x minus 1. But then we just have to multiply by the derivative of whatever the blob is. The blob is 2x minus 1. Its derivative is just a 2. So that's our derivative. It ain't pretty. It's something we could verify in Desmos, but I don't want to. I mean, just typing that in is going to be a nightmare. Might want to simplify it a little bit. I mean, if the only question that was being posed was find the derivative, I would just stop here and call it a day. But it's saying determine the points at which the function has a horizontal tangent. What that means is I have to take this, set it equal to 0, and solve. Sounds like fun. So horizontal tangent, again, is when f prime of x is equal to 0. We now know that f prime of x is equal to this whole mess. At some point along the way, it's going to be in our own best interest to simplify. But before we go too crazy with that, recognizing that when a ratio is equal to 0, that 0 could be thought of as 0 over anything. So why not let it be 0 over 1? When you cross multiply, the denominator at least goes away, which is wonderful. All right, so the denominator is now irrelevant. I'm going to get rid of this red here because it's a little distracting now. So this is the equation I have to solve now. One thing I would encourage you to consider, really at any point when you're solving a question like this, horizontal tangent, tangent line equations, anything numerical, it's not an algebra class. All right? You can do it algebraically. I'll do it algebraically in a sec. It's really not that crazy, even though it looks pretty nasty. But you can also type it in to Desmos and just see where it crosses the x-axis. All right? Whether you do it in this step or you take the full-blown disgusting derivative and plug that in, either way is fine. But the bottom line is, as long as you come up with the x value here, it's okay. Because again, I'm not concerned with the algebra. I'm concerned with the calculus. All right, but if we're doing it algebraically, the 2's would cancel. That's nice. This could be written as the square root of 2x minus 1 minus x over the square root of 2x minus 1. All right, because remember, fractional exponent, so an exponent raised to the 1/2 power, is going to give you a radical, just an ordinary square root radical, but because it's negative, it goes to the bottom of the fraction. All right, so then I'd have to solve this. Well, I can add this ratio to the other side, so I'd get the square root of 2x minus 1 is equal to x over the square root of 2x minus 1. Cross multiply, just pop this over a 1. You get x is equal to, well, when you multiply two identical radicals, it's the same as squaring the radical. Two opposite operations cancel away, just 2x minus 1. Subtract 2x from both sides. Negative x is equal to negative 1. Therefore, x is equal to 1. At long last. Now, again, not an algebra class. I mean, this is some fancy algebra right here. I mean, I did a great job, I feel like. Very, very, very appealing looking work. Not necessary, though. Okay, because the original function, again, x over the square root of 2x minus 1. If you needed to actually calculate the derivative, that's one thing. You have no choice there, so you had to come up with the disgusting derivative function. That's fine. But if you just need to figure out where it has a horizontal tangent, you take a look at the original graph, see where it has a turning point. That should automatically make you suspicious. Right? Desmos is kind of nice when it comes to that, because it'll plot turning points for you. Any instance in which there's a turning point in Desmos would be an instance in which there's a horizontal tangent. So tap on the function. Any gray dot that appears is either going to be an x or y intercept or a turning point. If it looks like a turning point, tap on it. Whatever the x value is what you're looking for. All right. So once you compute this, you've gotten credit for finding the derivative. Here you've demonstrated that you're looking for that derivative to be equal to 0. Take your derivative, set it equal to 0, and then just jump all the way down right to here and report your answer. All right, because again, it's not an algebra class. All right. And I'll shrink that down later and reorganize it. Now, if you want to actually see the derivative graph, That's fine. F prime of x that derivative graph should cross the x-axis somewhere if it's going to have a horizontal tangent. All right. Instances in which a function crosses the x-axis are instances in which the function is equal to 0. All right. So I would look to see where it crosses the x-axis. X-intercept, still a 1. All right. It's really as simple as that. So when you look at something like f of x equals the cosine of x, you really don't even have to look at the derivative graph. Because any instance in which there's a horizontal tangent corresponds to an instance in which there's a turning point. So you just tap on all those values on Desmos, and you'll have your answer. But you want to see how that corresponds with the calculus. All right? So that one, obviously, based off of the structure of it, you can tell doesn't involve the chain rule in any way, but it does reinforce this concept of a horizontal tangent. All right. So, again, numerical situations, the algebra is not necessary. All right. If you have to find the derivative because the directions tell you to do so, that's one thing, but they won't always tell you to do so. So be prepared to do it and just be thrilled when you don't have to. So for number 17, first we need the derivative, f prime of x. That's going to be equal to negative sine of x. For horizontal tangent, we want f prime of x to be equal to 0. So we're going to say negative sine of x is equal to 0. Divide both sides by negative 1, you get sine of x equals 0. So now, whether it's unit circle, inverse trig, or just looking at a graph, we need to determine any instance in which x would give a sine value equal to 0. All right. So if it's unit circle, it's easy because then it's just regurgitating facts that you've studied over time. But if that's not the case, what you would do is take a look at just the graph y equals a sine of x. Oops. And just identify any instance for which the graph touches the x-axis. So we have x equals, we got 0, we got pi. If we go out further, we have 2 pi, we got 3 pi. We got all that, but it could also go the other way. So we have a negative pi, negative 2 pi, negative 3 pi. So all these could be plus or minus. So what we would say is that there would be a horizontal tangent when x is equal to some multiplier of pi. All right, so there's going to be some number that we can multiply by pi that would account for every single possible instance in which the graph would touch the x-axis. So we typically call that k for some reason. And we just got to think about what type of number k would have to be in order to cover that. All right? So we wouldn't want to say all real numbers because that would be decimal values. That would get us every multiplier of pi imaginable. That would give us any point along the graph. All I want are 1, 2, 3, 4, 5, 6, all the way up to infinity. I want negative 1, negative 2, negative 3, all the way to negative infinity without all the decimals. So that's the set of integers. So what I would say is where k belongs to the set of integers. I mean, you could write it out verbally too, but you always feel fancier when you use the notation. But either way.